my or mute my audio so we don't have that extra buzz in the audio. So, all right, well, let's go ahead and get started. My name is John Mann. I'm a postdoc fellow at the North Central Regional Center for Rural Development, and I want to welcome everybody to today's webinar, Maximizing Bioenergy Production During Wastewater Treatment. Before we get started, I want to point out a few items real quick. And first, to the right of the screen, a lot of you have already filled out the survey on how you heard about the webinar. We appreciate that, and we appreciate the feedback. About halfway through the webinar, we're going to take about a minute pause, and we're going to pose a couple of trivia questions for you. It'll be just for fun. Then, as soon as the main part of the presentation is concluded, we'll have a question and answer session. And at the concluding of the question and answer session, we will have a couple of poll questions just to ask a little bit about your experience with university extension and technology transfer. And the next thing I want to point out is we're going to change screens a couple of times. And so I want to show you what this flash is going to look like. So I'm changing screens right now. At the conclusion of the question and answer session, there's a little guy at the very top of the screen. Looks like he's got his hand up in the air. And when you click on that down arrow, get about halfway or about most of the way to the bottom of the menu, there's an applause feature. And so when we wrap up with the webinar, that will be our way of giving Dr. Skidman a warm round of Adobe Connect applause. So finally, I'm going to click onto this last screen where we'll have the presentation. At the bottom of the screen, you can see the chat box. And during the course of the presentation, as questions come up, please go ahead and enter your questions into the chat box, and we'll get to those at the conclusion of the presentation. So again, I want to thank everybody for participating today. And with that, I'm going to pass it off to Dr. Skidman. He's from the University of Illinois, and he's going to tell us more about bioenergy. Let's go ahead.
Okay. Well, I want to thank you all for joining the webinar today. I think it's a great tool to be able to interact relatively easily across the country. I saw the title there on the slide, and I'd added in manure management. So wastewater here could be construed to mean both domestic wastewater and manure management systems broadly. I've got a couple of people here listed on the front slide. The first 6 are graduate students of mine who had some input on the work today, and so I wanted to acknowledge them. And then there's 2 professors there, Hank Wilkinson and Yan Hui Zhang, who are pretty close collaborators with me and are very involved with the work that I'll be presenting today. So with that, go ahead and go on to the next slide. Just in terms of a simple problem or opportunity statement, we start out with the fact that the U.S. produces each year about 50 billion tons of wastewater, manure, and/or food waste. And if you were to break that down a little bit, within that pretty much wet feedstock, there's about 200 million dry tons of biosolids. It would, in terms of an energetic contact, it would have about 3 quad per year of energy available. That's in the neighborhood of 3% of the U.S. energy demand, which is around 100 quad per year. And it would also contain about 6 million tons of nitrogen. So there's a lot of things there that are potentially useful. However, mostly today these things are treated or viewed as a waste to dispose of. And the basic question I'm going to try and answer today is, can we make better use of that material? Certainly there is some use made of that material today, but I think there is a lot more opportunity to do some good things with it. The next slide here just gives you a preview of the 2 major items that I'll cover, and then we'll go into the individual items. But the first one is looking sort of at a proven technology, which is to improve anaerobic digestion efficiency. And there are 2 main ways that I'll present on that today. One is through bioaugmentation, where we add specific microorganisms to the mixture of anaerobic digestion in order to increase rates and the biogas quality. And then the secondary thing is anaerobic digestion is usually just a step in the treatment process, and there is potential to do additional treatment steps that can provide other valuable co-products. And so we'll highlight some of those that I think are particularly promising. And then finally, the second part will deal with what we call environment enhancing energy. And this is more of a developing or novel technology. It's a combination of algae-based wastewater treatment that maximizes reuse of carbon and nutrients in order to sort of amplify the waste and have it make more bioenergy than was actually in the waste to begin with. And then the second major component of it is hydrothermal liquefaction, which is a sort of a generalist way, like anaerobic digestion, to turn biomass materials into usable biofuels. And in that case, it makes a biocrude oil similar to petroleum, which is obviously our most expensive form and our least plentiful form of energy available in the United States. And then finally, we've tried to design that system so it also maximizes water quality benefits. And one of the ones I'll highlight today is with respect to bioactive compounds like pharmaceuticals that are in our wastewater streams and estrogen products that have some undesirable, unintended byproducts and effects. So in order to get started here, let's see, John, can I adjust the... Hopefully everybody can see the whole
zoom
slide.
in for you just a little bit?
Yeah, I guess if they can see the slide, just the slide, that's probably the best. But looks like we've got a little bit of layover. Oop.
Let's do this. I know for us it's going to show up a little bit differently than it will for everybody else. So.
Okay. The other one wasn't bad. It just had a little bit of extra from the previous slide, so
Sure.
I guess I'd rather have a little bit extra than be missing. Right now I can't see the left side of the slide. So. Okay, so anyways, I guess to set a baseline here, we're going to start out with conventional wastewater treatment, just to say what we're trying to improve. And typically that system will start with raw sewage going into a primary clarifier, and that's where we just do a solids liquid separation by gravity. The clarified water goes into a secondary process, which is aeration, and this is where we pump in a lot of oxygen and let bacteria eat up the wastewater components that made it out of the primary clarifier. And then that water, which is got a lot of bacteria in it because that's what we grew in the aeration process, is clarified in a secondary clarifier. And then that material, after the bacteria settle out, goes into a discharge body like a river. The secondary stream, well, I'm having difficulties here. I can't move the arrow without moving the slide, so I'm gonna probably just have to talk this one through. The secondary stream here, the underflow of sludge, goes down into what's a digester, and that's an anaerobic digester, where that's converted into methane. Then those solids are subsequently removed, dewatered, and can be sent to many different applications. It can go to landfill, incineration, or agricultural reuse. This slide, which I borrowed, didn't originally have something showing where the liquids from the anaerobic digester go, but those liquids are not particularly clean. Anaerobic digestion ends up with a water quality that's not all that dissimilar from what went into the anaerobic digester. In fact, it can be worse in some cases, have higher organic content or higher nutrient content because some of the previously solid material has been dissolved and liquefied. So in any case, just to say that water that comes out of there is not clean. In particular, it has a lot of nutrients left over because the things that have been removed in the digester are carbonaceous materials that have been turned into methane. On the manure management side, Typically we have a simpler system, and this diagram here shows just the generation, then some form of storage of the manure, and then finally land application. At each of those steps there's an opportunity for nitrogen and phosphorus to leach out into the air or into the surrounding water bodies or into the groundwater. So that just gives you sort of the baseline for manure management. If we were to evaluate manure management, it's primarily done for low cost, because there's not the same kind of regulations on manure management as there is on a wastewater treatment outflow. And there's usually more land available in a nearby place where it can be effectively land applied and used as fertilizer. So in any case, most of the organics and nitrogen are removed or stuck on the land before they are discharged to any surface water body. Some of the nutrients are beneficially reused in crop production, and that sort of depends on when the manure is applied and some of the environmental conditions. A lot of it is also often lost to nitrate that goes into the groundwater. The energy content of the manure is pretty much dissipated without use, so microbes will work in the soil to turn it into CO2, so you don't get any bioenergy benefit out of that. There are, as I mentioned, some nutrients in the organics that are lost to air or water, and those lead to some environmental problems mentioned there as odors or eutrophication and hypoxia. And then there are bioactive compounds I mentioned earlier, and those are discharged to the water body in some extent. I mean, there is removal on the soil via absorption, but it is quite common to find downstream of a wastewater outflow or a manure outflow to have extra antibiotic resistance or fish feminization due to estrogenic compounds making it into the surface water. So those would be things we'd like to avoid if we could. If we compare wastewater treatment and manure management, overall with wastewater treatment there's more organics and ammonia removed before the water is discharged. There's less bioactive compounds discharged with wastewater treatment, and there is some bioenergy recovered with wastewater treatment. However, the downsides are that you're using much more energy for the treatment, in particular the aeration is a significant energy burden for the wastewater treatment process. Less of the nutrients are beneficially reused in crop production, and therefore more of them contribute to eutrophication and hypoxia. And then finally, it's a much higher cost system. You're trading capital costs for the lower environmental impacts. And so anaerobic digestion of manure is used, so it's not to say these are either or situations, but typically it needs a grant or a subsidy to make a positive return on investment. And so there are many programs through the USDA that support the building of those digesters for manure systems, but there's not the same impetus that there is in the wastewater treatment field, which is under stricter regulatory scrutiny and typically has to have something like the digester to reduce its waste output. Okay, the next slide here gets a little bit into the mechanisms. I won't go deep into this, but I just want to give you an idea of how we're trying to improve anaerobic digestion. And in order to do this, John, are you any more able than me to get that lined up?
Yeah, let me try just real quick.
Okay, yeah, that's good. Okay, so bioaugmentation is attempting to improve some of the desirable rate-limiting steps of anaerobic digestion. And what you see at the top here is that you've got the original waste material classified as proteins, carbohydrates, or lipids. And those materials go through a series of breakdown steps. The first one is hydrolysis, to put the material into a solution where it's accessible by microorganisms. Then it's fermented into volatile fatty acids, particularly propionate and butyrate. And then finally, there's a process called acetogenesis that makes acetate, and it can also result in a co-process there that makes hydrogen and CO2. And And then finally, the last step, which you're after with an anaerobic digester, is methanogenesis, which turns the acetate and the hydrogen into methane. You'll see over there to the right there's an undesirable pathway which can interrupt that flow of material, and you make hydrogen sulfide, which is the rotten egg odor commonly associated with anaerobic systems, and that reduces your energy output, and it's also toxic to some of the organisms that are trying to make your methane. So it's something you'd like to avoid as much as possible. And what we're going to do with bioaugmentation is try and help out with the hydrolysis step by putting in organisms that are good at that. We'll try and help out with acetogenesis, because that's another common rate limiting step, to make sure that process is expedited. And then in doing those two things, we decrease the amount of material that's processed through the hydrogen sulfide pathway, because we're not augmenting that particular pathway. So it's not that we're eliminating it, but we're just encouraging the other pathways and end up with less material going down that route. Okay, so the next one here shows what I would call an integrated multi-stage waste treatment system that in this particular case was applied to fish waste from indoor aquaculture, but it could also be applied to any other bio-waste stream, such as manure or municipal waste or food waste. But the basic idea here is that you start out with the concentrated fish waste material coming off the bottom of the aquaculture tanks. And the first step you want to do is anaerobic digestion to get as much energy out of that material as possible. So you're primarily removing carbon and hydrogen in that step. You make a biogas, and then the biogas is used for heat and electricity. You would also make a fertilizer compound, or you could make a fertilizer out of the biosolids that come out of the anaerobic digester. But then we're adding some steps to that, because I mentioned that anaerobic digestion usually doesn't give you a good quality of water, leaves behind a lot of nutrients, and actually leaves behind a fair amount of organics as well. So the remaining organics that weren't harvested in that previous step are, in this case, turned into a single cell protein product, which is basically we again bioaugment with a specific approved bacteria for feed products, and so we go ahead and grow that bacteria on the leftover waste material, and then that's harvested, and you can see it moves into the feed mill on the left-hand side, lower part of the diagram. And then the algae part of it, after you've done the anaerobic and aerobic digestion, what's mostly left is nutrients in the water, and of course algae can use those nutrients, combine it with carbon dioxide from the atmosphere, do photosynthesis, and make new biomass. So in that particular case, you would take the algae again, and that material gets put into the feed mill, because both single cell protein and algae are good for fish food, and they're good for a lot of other feed products as well. We may have time to talk about that a little bit more later. So in order to make the most out of our bioaugmentation system, we went with what's called a two-phase anaerobic digester, where we separate the acid-producing reactions in the first phase over here from the methane phase reactions. And the methane phase typically likes to operate at a higher pH and a longer retention time than is necessary for the acid-producing phase. And so, although anaerobic digestion is commonly done all together in one tank, it can be done more efficiently if it's separated into two tanks. And in this particular case, we're bioaugmenting, as I said, and so we add in the proprietary facultative bioculture into the acid phase process. And what that does is it increases the amount of VFAs being produced that go into the methane producing stage, and it also reduced the amount of hydrogen sulfide. And so when you do those two things, then the final effect is that it increases the biogas that can be produced. I also have here that we've put some solid media that's shown by these little X's, circled X's, that help to encourage the methanogens to stay in the reactor because they're slow growing. And so if we keep them in the reactor, then they can do their job better and faster. Okay, so how does this bioaugmentation work? This is a simple batch test, so you can sort of clearly see the results. And in this particular case, we've got theoretical methane production shown up at the top. Let's see if I can get there. Okay, and then we've got two curves shown. The first curve is with bioaugmentation. Having difficulty getting down there. But in any case, with bioaugmentation, you can see that we got very close to the theoretical methane production, and you can see then just below it is the line for non-bioaugmentation. If I can get there. And in that case, it's about 20% lower in terms of the maximum amount of methane produced. That comes at least partially from the diversion away from the hydrogen sulfide path. But you can also see that the kinetics are faster. So if you go back a little bit here, you can see that the kinetics are about 40% faster as you approach the end of the digestion for the bioaugmentation phase. So it does work, and it's a notable improvement. I mean, if you go 40% faster, that means your reactors can be 40% smaller, and if you get 20% more methane, that's a significant amount of additional product that helps the economics of anaerobic digestion. Okay, so we also in this particular case did a longer term pilot, and I'm going to go ahead and turn off the pointer here. But basically on the left hand side there you see bioaugmentation in a darker blue line going up and sort of leveling off in terms of methane production. And then we turned off the bioaugmentation, and you can see that it starts to decline and goes down to a lower level. So that's a pretty significant loss from around 275 mils per gram of volatile solids down to around 200. Then we had a switch in the fish waste batch, because with waste material, of course, it's not uniform every day. And so with that particular material, we started out with no bioaugmentation, and you can see the steady state production in a lighter purple color. And then you can see it increase over there to the right as we turn the bioaugmentation on. And so in both turning it on and turning it off, bioaugmentation had a beneficial effect. And then finally, down there at the bottom, we're just showing for these same four conditions what happened with hydrogen sulfide production. So you can see hydrogen sulfide production going from the darker blue to the lighter blue stepped up a little bit, and that's due to turning off bioaugmentation. And then for the step down from no bioaugmentation in the light purple to bioaugmentation in the dark purple, we ended up with a reduction in hydrogen sulfide there. So again, it was doing what it was supposed to do, and that's the actual data. When we looked at the bioculture dosing, we gathered some data that's useful for confirming the mechanism. So in this particular case, you can look at the blue line, which is the total volatile fatty acids. And you can see as we increase the bioculture dose from 0 milligrams per liter on the left-hand side up to 400 milligrams per liter and then 500 milligrams per liter, there was a steady increase in the volatile fatty acid production. And then we actually, towards the end of the test, stepped it back down to 300 and 200 and sort of showed that we could back off a little bit on the dosing of the bioculture. But pretty much the biogas, which is shown in the green, and the methane, which is shown in the red, tracked with the VFA production. So it's just as we expected. As you increase the VFA production, you get more biogas out of the system. Study 2, we've done this with many different wastes, but this one was with a cellulosic kind of waste, which is more difficult to degrade. And again, we can highlight here in the lower left-hand corner that we had a situation. It's not showing up here, but the first part of the graph is with bioaugmentation. Then the middle part that shows a lower cumulative methane, that's dropping off, is without bioaugmentation, and then we turn the bioaugmentation back on, and again, the increase occurs for the bioaugmentation in terms of methane production. And then towards the top here, we have the volatile fatty acid data, and it just sort of confirms the same thing, that we see volatile fatty acid increases with the bioaugmentation, decreasing without the bioaugmentation, and then re-increasing as the bioaugmentation kicks in. The reason we don't get quite as quick a recovery when we turn the bioaugmentation back on is because the methanogens do take a while to grow. So although we've increased the VFA production, it takes the methanogens a while to catch up and sort of grow to their steady state biomass levels and achieve equilibrium with the VFA production. Okay, so I also mentioned that there are other co-products of interest. So in this particular case, I'm highlighting one called a peat moss replacement. And in this case, we're just taking the anaerobic digestion solids from a crop residue, and that material turns out to be a pretty good replacement in terms of its physical properties for peat moss. And then this is a picture here shown from a USDA study that we compared the peat moss replacement, the anaerobic digestion biosolids, 100% 50-50 mix with vermiculite, and a 50-50 mix of peat moss and vermiculite. And you can see the tomato plant in that particular situation grew much better with the peat moss replacement product as opposed to conventional peat moss. So it's just highlighting it as, in that case, having both a fertilizer value and a soil amendment kind of value. And then I'll just mention one ongoing study that we have that continues some work in this area. The first part of it is, and this is done for the DoD, focused on domestic wastewater, particularly for Army bases. But the first part, we're demonstrating the membrane bioreactor in the anaerobic digestion phase, and that just allows us to further shrink that reactor and make the process go quicker because we're holding the methanogens in perfectly in the reactor. And then we're also working on developing customized biocultures that are tailored to the specific waste. We have some proprietary formulations that work pretty well for a lot of different wastes, but we can sort of tweak. We've got a process for tweaking it and making it custom to any particular waste stream of interest. In year 2, which is starting now, we're going to incorporate some adsorbents into the anaerobic digestion process, and that just, again, helps with the speed and efficiency and make sure that the water quality is as high a quality as possible going out of the system. It also helps with reliability and dynamic loading conditions, which are common in wastewater treatment situations. And then the third year, we'll look at some comparisons with other advanced bioenergy processes. First one, catalytic hydrothermal gasification, which is another process for making methane, but it's doing it through a thermochemical route instead of a biochemical route. And then there's a process called the green box that's being commercialized for converting ammonia into nitrogen gas and hydrogen gas. It's electrolysis, very similar to what you have with splitting water, and then the hydrogen that you get out of that process is worth more energy than the energy you put in. So that's the idea with that. Okay, we'll finish up here with this anaerobic digestion portion, and we've got co-products from a comprehensive waste management system ranging from soil amendments, algae products, high protein feeds, get recycled water, you could potentially have carbon credits, and then of course heat and power, which is where we started. And then in terms of commercial needs and opportunities, we're currently partnered with Microbial Energy Systems out of Bloomington, Indiana, and I've given the main contact there, Dr. Richard Wagner. There is some intellectual property that's related to the bioculture formulations and the novel co-product applications like the peat moss replacement. There is a need for biowaste producers for application development, so obviously we want these systems to go out and be used, and we have to sort of develop those applications one at a time. If you have an existing anaerobic digester, we can retrofit into that, and that's probably the easiest way to do this. Probably what we're most focused on right now. But it also can be used for new systems. You'd start out with some sort of a pilot study and then eventually go up to a full-scale application. There is USDA grants available for cost offsets on a lot of these kind of programs if you're an agricultural producer. And then there's also some need for entrepreneurs and investors in market development. In particular, we want to have a mobile pilot system that could be brought out and sort of shown how the system would work at a particular application. And then we continue with what we call the Better Bugs program, which is continued R&D for improved and customized biocultures. And then I just wanted to give you one idea of how this shakes out economically. And this is done by MES, so I can't take credit for this particular part of it, but it gives you an idea of how it would work. So if you had a 1 million bird poultry facility, you might produce something like 100 tons per day of manure that has 75% moisture. Your capital cost was estimated for that system at about $4 million. The electricity value that would be generated is around $1.1 million. The heat value around $485,000. The organic fertilizer $250,000, and then the single cell protein value at around $60,000. And then you have some savings with respect to reduced waste disposal. If you compared that to a conventional anaerobic digester system, the capital cost would be reduced about 25% due to the increased rates, and the product values would be increased by about 95% due to some of the extra products and the extra amount of methane that you can get out of the original anaerobic digestion with bioaugmentation. Okay, so I think I'm going to take a break there and do the questions before we launch into the second part.
Okay. So far, this has been a great presentation, Lance. Thanks for this. And I'm going to open up a couple of trivia questions. They'll be pretty straightforward, pretty simple, based on what we've seen in the presentation so far. And if you'll take just a moment and look at those, I'll give you about a minute. Make sure you can see these. About another 15 seconds. Anybody wants to change their answer at the last moment? Okay, well, I'm going to look at my cheat sheet here, and the answer to the first question is A. Just about everybody got that one right. Municipal and domestic sewage. The answer to the second question, according to my cheat sheet, is actually C, between 1 and 10%. Good questions, and thanks for your answers to those.
Yeah, I'd like to comment on that first one.
Sure.
I made it was a little bit of a trick question with the wastewater. If you focus on the water component, municipal is definitely the biggest producer of wastewater. But if you focused on the actual biosolids component, manure would far outshine all the other processes listed there. So whereas municipal biosolids would be in the 25 million ton per year range, manure might be in the 125 to 150 million tons per year. So the right answer was domestic sewage, but livestock waste could have been, if you considered it from the solids perspective and the energy perspective. There's more energy and more solids in the livestock waste.
Well, Lance, I'll go ahead and let you get back with the presentation.
Okay, sounds good. On the next part of the presentation, I'm going to focus on what I called emerging or novel technology, which doesn't just sort of tweak what we're already doing today and try and make some improvements in it to make it a little bit better. We're sort of throwing everything out and starting over and saying, if we were going to design this system to maximize bioenergy production, how would we put it together? And so I'm sort of giving you the answer here with this first slide, is this process we're calling environment enhancing energy. And it really starts out very similar to the wastewater treatment plant, where you go through a liquid-solid separation. But in this case, the biosolids go down into a different process, which is termed here as hydrothermal liquefaction, or HTL. And the reason we've chosen that process is because instead of making gas, which has lower value and it's harder to transport around, you can actually make a crude oil product similar to petroleum with the hydrothermal liquefaction. Then at the same time, we're taking that dilute liquid, and instead of going into an aerobic bacteria growing process, we're going into something that encourages algae cultivation. And the reason algae is preferable is because it introduces new energy. We're harvesting sun energy into the waste, and we're using the nitrogen and the phosphorus and other nutrients to basically leverage the amount of biomass feedstock for bioenergy production. Of course, we have sunlight and CO2 inputs that are needed for that. And then we go through an algae separation, and then we bring that algae separation back into the hydrothermal liquefaction process to produce more biocrude oil. You'll see that in the middle here I've got this multi-cycle nutrient reuse, and this is really the powerful concept of this particular alternative wastewater treatment system, in that when we bring the algae back into hydrothermal liquefaction, what happens is that the material is turned into oil, and the nutrients are re-released into the water component of the material that enters the HTL reactor. So essentially, the nutrients sort of spin around in a circle, and you can grow not one cycle of algae, but actually grow multiple cycles of algae based on one set of input nutrients. Now, it's not perfect in terms of the recycle. Some of the nitrogen does slip out into the biocrude oil. Some of the nitrogen does slip out into the treated water. But we can maybe use it somewhere in the range of 3 to 10 times. So that means you can amplify your biomass by 3 to 10 times, and therefore your bioenergy. I should say that this technology has been patented through the university and then licensed to Snapshot Energy for commercial development. And we'll talk a little bit more about that later. So just to say a few words about algal-based wastewater treatment, it actually isn't pure algae that we're growing in this system. We're growing algae and bacteria together, and this diagram just sort of shows that they work nicely together because the algae produce oxygen that the bacteria need. The bacteria break down organics, which are present in the waste, and produce CO2, which the algae need. And so this is what happens in nature, and we're just sort of using that model and trying to encourage it and make it happen as quickly as possible. Why don't we use more algal wastewater treatment systems? Currently, there's no use for the extra biomass. That material is mostly being land applied, and so it's a cost-negative endeavor usually to get that out to the fields and applied. And so people right now, because they're focused on the aerobic systems, are not necessarily interested in making extra biomass. The removal is more dependent on light and temperature and other factors than bacterial biomass, and so there is it's a little bit more difficult to operate than a conventional wastewater treatment process. The Clean Water Act sort of pre-selected that activated sludge or bacteria-based processes would be what's instituted, because that's what loans were made for, or grants. And then finally, at the time when we made most of our wastewater treatment systems, energy was considered plentiful and cheap, so we didn't really have an interest in harvesting as much energy as possible out of the wastewater. But that is no longer the case from most people's perspective. Okay, so there is a synergy, though, between algal biofuels and wastewater treatment. So algal biofuels is a very hot topic. and there was a roadmap that was done by the DOE in 2010 that noted that algal wastewater treatment wastewater treatment and recycling must be incorporated in with algal biofuel production. And in fact, it also noted that nutrient recycling would be needed, which we were getting from that multi-cycle nutrient reuse feature that we mentioned earlier. And because even though there's a lot of nutrients in our wastewater, there's not enough to produce the amount of algae that we want to make if we're only doing it on the basis of single-use nutrients. And then there's a quote down there, a couple quotes from President Obama in a speech last year talking about algal bioenergy. And I'm not sure exactly where the 17% came from, but actually I'll try and make the case here today that we can do a lot better than 17% of our oil based on the system that we've proposed. So what are the problems with current algal biofuel paradigms? This diagram at the top is sort of showing the way algal biofuels is conventionally done. You have a culturing operation where you grow the algae, then you harvest the algae into a cake, then you dry the algae out, and then that algae that you were trying to grow typically has an oil component, and so you try and extract the oil, and then you can convert that to biodiesel, similar to how you would do with soybean oil. The problem is that if you do this path, which is done for soybeans, you spend a lot of energy on drying because algae is a lot wetter than soybeans and other terrestrial feedstocks. So we have a problem with energy balance if you try and go the normal route, and there are currently lots of people who work on wet extraction methods to try and avoid that step. You also run into a problem with contamination, especially if you do this at large scale and in waste treatment systems. You start growing one high oil algal species, but you end up with some other low oil algal species or rotifers or bacteria or some other contaminant in your system, and you don't end up with a lot of oil, and then the rest of the process sort of breaks down because there's no oil to extract and convert. And then finally, there's some cost and environmental impacts because you're using a lot of water and a lot of nutrients and a lot of CO2. So to look a little bit closer at that energy balance problem, you can see this particular graph here shows the different steps and what amount of energy is spent on those steps. So you see that drying is in fact the blue part of the bars here is the biggest energy input, and the arrow growing across there shows the energy content of the biodiesel that you're ultimately producing. So if you're at or above that line, then you've got an energy negative process, which of course is not good for bioenergy production. So you can see there's really only one option here that works, which is the wet extraction type of methods with low nitrogen feedstocks, and in that particular case you can make a positive energy balance, and so we're doing something that would fall into that general realm, although I think we can even do better than what's shown there. But the lessons here are that you must process wet, dewatered biomass. You can get it partially dry like a cake, but you can't dry it out into a powder. If you do, you lose the energy balance. And it's much better to use wastewater nutrients if you want to have a positive energy return and a positive economic return. The other problem that I mentioned was contamination. And the problem here is illustrated by this figure, which shows the relationship between growth rate of the algae and lipid content. So you can see that there's a general negative correlation between those two for lots of different species and lots of different studies. And basically what we have here is that if you try to grow the high oil species, they generally will grow slowly, and they will be outcompeted by the low oil species and everything else that can eat algae along the way, which is lots of things. And so the bottom line here is that the bioenergy process needs to utilize low lipid biomass. And that's definitely much more consistent with wastewater treatment as well, because you have less control over what you're growing. And so you just want a very generalist system that can handle lots of different kinds of biomass and turn them into oil, which is what the hydrothermal liquefaction gives us. Okay, so there are 4 basic steps of the E-squared energy process which we've confirmed at the bench scale, and I won't go into the data for those, but I'll just tell you what the steps are. First, we have to be able to grow the algae in a mixture of raw wastewater and post-liquefaction wastewater. The organics and the nutrients have to be removed and taken up during the algal biomass production. Then we have to be able to convert that low oil algal biomass grown in a wastewater treatment system into oil via hydrothermal liquefaction, and we have to go ahead and then show that when we do that liquefaction, we re-release the nutrients and can repeat the cycle all over again. And we've done all those steps. If you want to see some data, you can ask questions about it afterwards, but I couldn't cover all that data for the sake of time on this particular thing. But we have shown all 4 of those in a proof of concept kind of way. So then the next step is to see what would happen if we did this over a long period of time and had all of the internal steady state recycling going on. So we have a fairly, it's actually a fairly complicated model that we've put into the Stella modeling platform, but it looks simple on this particular slide where we have feedstock pre-treatment, which is the settling tank. We show algae going to the top, liquefaction going to the bottom, and then there's a series of things that are traded back and forth between the liquefaction and the algae cultivation. And ultimately what comes out is bio-oil, some residual ash product, and treated water on the top part of that curve. So when we implement that model, it looks like this. This is actually just one of the components of the model. These are all the equations that are involved. And then this is what the model looks like in its visual format, if you're familiar with Stella. But that's probably, for this crowd, what you want to see is the results, which hopefully will come up here on one of these slides. I'm missing one slide here in the middle, but the results are also represented on this mass balance slide, which comes next. I can get it up. There we go. Okay, so this is just showing the components of the process, and we start out over on the left-hand side. I'm highlighting that we've got about 91 kilograms of carbon coming into the system, and then there's 267 kilograms of carbon that's coming in through the atmosphere. So again, this is the new energy harvested into our waste treatment system. And then at the end, we're able to produce about 495 kilograms of oil. So you can see that we're able to actually make significantly more oil than we started out with in the original waste. If you were to look at that for a 10,000 head swine farm, and I've also done municipal applications too, but for this one, if you start out with 5 tons per day of manure production, and then you went ahead and went to, instead of, well, you harvest some of the energy into hydrothermal liquefaction, go to oil, but then you recycle the remaining material and nutrients into algae production. Based on the modeling that we've done, I mentioned that you could make somewhere between 3 and 10 times the amount of biomass coming out as what went into the system. And so that would be 15 to 50 dry tons of mixed algal biomass, which when converted through hydrothermal liquefaction would be somewhere between 30 and 200 barrels per day of oil. And so for a 10,000 head swine farm, if they made 100 barrels of oil a day, and that was $100 a barrel, that would be $10,000 a day of output from their waste treatment system, which is pretty good. And in the case of a municipality, it could actually supersede the entire municipal budget for a town. So let's think big here. And if we start out with the fact that we've got these 3 waste sources that contribute about 2.2 billion dry tons of nutrient-rich biosolids, And actually, there's other sources. We could go to the paper and pulp industry. They've got a lot of organic material, and there are other sources as well. But these are three big ones. And if instead of doing what we're doing today, which is just sort of treat it as a waste product and try and get it out into the environment as quickly as possible, if you instead went ahead and produced algae, you could grow somewhere in the range of 0.6 to 2 billion tons of mixed algal biomass. And then if you were to convert that into oil via the liquefaction process, that would make between 0.3 and 1.2 billion tons of biocrude oil. So that's a big number. How does it compare? Well, our total U.S. oil demand is around 1.1 billion tons of crude oil per year. So we have the potential, and I realize it's a long way off and it's a far-reaching potential, but you have the potential to actually make the full amount of oil based on waste product inputs if you were to go through this system. If you compare that to what we've done with corn going to bioethanol, right now we use about 40% of our U.S., well, up to 40% of our U.S. corn to make about 0.06 billion tons of biofuel. So you can see there's much greater potential in this case than we have with corn. Now, a really key question is, do we have enough land to grow the algal biofuels? And I borrowed this slide from the DOE showing the land needed for biofuel to replace 50% of current petroleum diesel using corn, which is the yellow box, soybeans, which is the gray or brown box, and then algae, which is the small green box. Now, of course, there is discrepancies between researchers as to how much algae you can produce per acre. It's better than all of the other choices that we have, but your range of estimates may go from that little green box to maybe a box about the size of Nebraska, which I've shown there in the middle. But in any case, it's less land than we're already devoting to bioethanol production, and so I think it is a feasible amount of land to make a substantial amount of our biofuels from. I just have one slide here on some of the side benefits in terms of water quality. When we go through the hydrothermal liquefaction, we have good destruction of many of the emerging bioactive contaminants. So this one looks at estrone and then 2 antibiotics that are commonly used in livestock production, and shows the removal under 2 different HTL conditions, 250 degrees Celsius and 300 degrees Celsius, and then 3 different retention times, 15, 30, and 60 minutes, which is the amount of time we need to do the oil production process. And you can see that if we go towards the higher end, 30 or 60 minutes and 300 degrees, then we pretty much have complete removal of those bioactive compounds. So we're getting an additional water quality benefit that we don't get today with conventional wastewater treatment and anaerobic digestion. So some next steps on this particular piece of work. But right now, I mentioned that we've done the steps in a piecewise format in different labs around campus. We're now going to bring them all together into a common demonstration project on the campus swine farm. So you can walk into one place, see the swine manure going in, see the algae growing, see the wastewater solids and the algae being turned into oil with hydrothermal liquefaction, and then recycling that material back around for another cycle of algae growth. And so that's we've got the building completed over the winter, and we've moved the equipment out there and are sort of starting up operations. Some commercial needs and opportunities here. I mentioned the original IP was licensed to Snapshot Energy, and I've given a contact here if you want to check in on further developments. They've raised through Snapshot about $500,000 for the phase 1 demo, which in the end will produce about 1 to 3 gallons per day, and to do some design work on phase 2. The phase 2 is expected to make about 1 to 3 barrels a day, and the expected cost for that is around $3 million. So at some point we'll either have to get a grant for that or raise some more money. So obviously there's need for entrepreneur and investor input at that point. And I would say, I mean, right now we're pretty focused on phase one, but phase two will planning will occur during this year, and hopefully implementation sometime next year. And then we're always looking to develop strategic partners, bio-waste producers that are interested in application of this technology. There is a need for upscaling of the HTL equipment. Currently, that's not a piece of equipment that's readily available and off the shelf. So there are attempts that have been made, but I think this is still a hole in the market. And then bio-oil refiners and bridge market development. So one of the issues we think we'll run into is that you can make this bio-oil, you'll make many barrels of it, but in order to get a refiner really interested in it, you have to make hundreds of thousands of barrels. And so there's a little bit of a chicken and an egg question there. Can you make it before somebody commits to taking it? Can you get somebody to commit to taking it before you make it? And so we think there are some bridge products, bridge markets through asphalt, bioplastics, and heating oil that we are planning to develop in order to help bridge to those really large quantities that are necessary for refinery scale work. And with that, I've reached the end of my presentation, and appreciate your time.
Lance, thank you so much for that. That was a really good information. So if you've got questions, go ahead and take a moment and put those into the chat box, and I'll read the questions off one at a time and give Lance an opportunity to answer them. And I've got a couple of questions of my own, but the first down here, and I also want to note that we're coming up close to our 1 hour for the webinar, so it looks like we might go over just a little bit, but we'll get to everybody's questions if you've got them. So this first question, let's take a look at it. And so it's from Fran Lou, and she's asking about an issue with I guess a nuisance of odor at a public school, and sorry, I'm having just a little bit of technical difficulties here. I'm going to modify this screen just a little bit so I can actually see these questions and let people be able to type at the same time. So bear with me for just a moment. I apologize for the technical problems that we've had during the course of this presentation. Okay, so the question is, so let me just read this off. So it says, I have been tasked to assist the public school nuisance odor problem due to municipal waste treatment plant literally next door. It says our team is looking for novel ways to first reuse a portion of the energy to generate power, and especially to rid the school of the noxious smell. And then she says, I assume from the hydrogen sulfide, based on what you presented, looks like your system would be great for us, and maybe from like a showcase. And so, so if you want to just kind of talk about that for just a minute, what do you
Sure.
think about that, Lance?
Sure. Yeah, I think that I'm not exactly sure where the odors are coming from in the wastewater treatment process. Usually the aerobic digestion, if it's being handled properly, doesn't have a very foul odor, so there's probably some parts either early or late in the system where odors are escaping from anaerobic systems. I think with any anaerobic digester or the hydrothermal liquefaction process, we are going to have some off-gas product. And if you really want to have a no-smell wastewater treatment plant, you just have to capture that gas, put it through a activated carbon bed, and then let it out. So it's feasible. The big advantage here is that you would have some additional revenue that could help pay for that collection and treatment effort. Whereas with the current system, it would be cost that you're spending, but you're not getting any benefit out of it. And so I think that would be the the primary advantage. With the second system, there would be some additional advantage in that relatively little amount of the waste ends up in the gas product from hydrothermal liquefaction. So there's a smaller amount of gas coming off of that process, so the amount that you have to treat is smaller in that case, significantly so, maybe by a factor of 10 or 20. So I guess those would be my initial thoughts, and I see you had there, you may be interested in some follow-up, and I'd be happy to talk with you offline about that.
Okay, so our next question is, it says, are the diatoms routinely expected in your Agile lineup?
Yeah, so actually we do see some diatoms, but it's not the most common thing that we see in our wastewater treatment systems. They're commonly limited by silica, so if you happen to have a lot of silica in your water for some reason, then you'll get more diatoms. We don't try to encourage the diatoms because silica is essentially an ash product, so it moves through your system, and you can still do the hydrothermal liquefaction, but you have a higher amount of ash product because of the skeletons associated with the diatom. So it still works, but it gives you a little bit more of a byproduct to deal with in terms of the ash product that comes off. So my preference is to go for green algae and or for cyanobacteria, but if you get some of the other components, they can be converted into oil. In fact, this is how our original oil was probably made: is that sea-based biomass, largely algae, was deposited at the bottom of the ocean, subjected to heat and pressure, and turned into oil. So we're just following Mother Nature's lead. We're just trying to do it in a expedited, engineered fashion.
Okay, so the next question is there a way to monitor remotely the biogas production and other inputs that increase the methane production?
Yes, yeah, there is. The Europeans have done more with setup of small-scale anaerobic digesters, and therefore have had a greater need for remote monitoring and control of the systems. We typically do anaerobic digestion at the wastewater treatment plants or at a very large livestock production, and so they are the remote monitoring is not as big a deal there because you've got personnel on site all the time. But it certainly would be possible. In the smaller scale that you get to, the more advantage there would be of that you could have centralized control, and then you could run somebody out to the plant if there was a problem or the computer had some issues that it wanted a person to take a look at. So yeah, that's definitely it'll become more of a need as you go to more and smaller applications and waste generation sites.
Okay, so the next question is about the desulfurization and the use of extremophile bacteria and I guess this algae.
Yeah.
How about the use for the
algae are in general very sensitive to sulfur. So if you're going to use power plant flue gas as your feedstock for CO2 supply, which is a nice combination. The one thing you do have to do is do some sulfur treatment to get the sulfur out of the flue gas, because the algae are relatively sensitive to it as a whole. I'm not that aware of extremophile bacteria that are good for desulfurization, so I'm not sure I can comment too much on that. When we were talking about the anaerobic digestion, my general goal was to try and avoid the sulfur production, because it reduces our energy. It is a part of a common biogas cleanup. You just put it through some iron filings, and you can pull out the sulfur. So it's not a process problem. There are good physical chemical processes for dealing with it. But if there's some ways to get additional biomass out of it through the extremophiles, that would potentially be interesting, because we can use that biomass for bioenergy production.
Okay, the next question, it's also from George, and I'm not sure quite how to frame this, but it looks like it's related to high temperature anaerobic digestion, 130 degree Fahrenheit range.
Yeah, I mean, I've not worked in that high of a temperature range. We almost always work in the mesophilic range. Occasionally, we've worked in the thermophilic range up to maybe, well, I guess you could get up pretty close to 130 with that. But but yeah, the most of what we've done has been at the mesophilic range because the bacteria are a little bit more robust and hardy in that range. The thermophiles are maybe a little bit more efficient, but they're a little bit more. They're generally known to be more fussy, and you've got a parasitic energy load to get up to that higher temperature that's greater. So usually the balance can be made, but it is a trade-off with the mesophilic temperatures. If I didn't answer your question, feel free to shoot another one back. But those were the thoughts that came to my mind based on the words on the page.
Okay, real quick, I've got one of my own, and again, since we're out of time, I'm going to kind of keep my question quick. But okay, so based on where you're at with some of the technology production, I know you talked about it a little bit, but can you give me a little bit more information about maybe what type of an organization you might be interested in working with some of the bioenergy production? So if I were to try to identify somebody or say, hey, this is kind of what we're looking for, what are you looking for in particular?
So on the anaerobic digestion work, we probably are at the stage where there's need for capital input in order to develop some of the marketing systems, like I mentioned, the mobile pilot development, and getting somebody to go out to conferences and talk about the systems for groups that are involved with waste production or anaerobic digestion already. There's continuing needs on both parts for research and development, but that's always the case. And the bottom line is we seek that money through grants, and then occasionally it gets close enough to application that an investor wants to jump in and make it go a little bit faster. So we continue to make progress in that area, but if there are investors who want to see sort of the next generation of our systems, then there's always an opportunity there as well. And then on the E-squared energy, I think probably the biggest area of need right now is in the co-product market development. So working with strategic partners on refining asphalt applications is probably the immediate area of need. And then shortly after we're done with the phase 1 and or phase 2 demonstration sites, then we would need to have waste producers, so whether it be a livestock operation or a food processing plant, that would be, you need to have the feedstock in order to get the system started, and so those would be important contacts to make at this point, although I think we're still a year or so away from moving out to start planning for field applications.
Sure. Okay, I'm going to flash screens real quick, trying to answer your question. So if you look in the lower right-hand part of the screen, I've got a couple of emails popped up, the web links, and so Dr. Skidman's email is up there, and my email is also up there. So you're welcome to email either of us, and I'll make sure that it gets forwarded to Lance. And with that, it doesn't look like we've got any more questions. So if you recall at the beginning of the presentation, I wanted to be able to give our presenter an Adobe Connect applause. And so that little guy at the top, you can click on that little arrow and find the little clapping hands. And also there are a couple of questions we've got to pose, and I hope you will take the time to answer those. And that, again, if you've got any other questions, I'll stay on here for just a little bit, and Lance, if you're okay, kind of look through here and see if anybody else has got anything popping up.
Yeah.
So it looks like Carlos is typing. Okay, thank you. Thanks again for your participation.
Yeah, thanks to everybody for your time today, and I hope that you found the information useful, and look forward to talking with some of you in the future.
It looks like we've got a couple of folks here, Fran Lou and also Mike Marshall
Okay.
to contact.
So I see the question about water in the open tanks, and yeah, I mean, yes, conventional wastewater treatment is typically done in open tanks. There will be some there was some latitude at which you will need covering on the tanks. Conventional wastewater treatment plants throughout the U.S. don't generally have to have covered tanks because the wastewater has enough heat to keep them from freezing. But we're going to spread the wastewater out over a bigger land area, and so there is a potential for needing to cover some of the algae cultivation tanks during part of the year. My anticipation there is that it would be approached more in an agricultural way, so we'd have some sort of low-cost hoop house kind of structure with plastic film over metal supports, and so it's not a complicated structure, but there would probably be a need for something like that above a certain latitude, and I'm just not exactly sure where that latitude is, where the heat balance would lead to freezing. And then you mentioned there was one from, who was the other question from?
There was a comment from Mike, and I think Brian Wilson has expanded a little bit, so we can read through that real quick. Okay, good. Brian's good. It looks like he's got your contact information. Thank you for that. And I think well, we'll let Brian here type his question real quick. Okay. So we were planning to develop the AD on the domestic scale. It sounds like that you two might need to have a conversation on the phone.
Sure.
Talk a little more in detail about what's going on.
Okay. Yeah, I mean, I'm in general support of bioenergy applications, especially those using waste, and so if there's something that I can help out with on that, then I'd be happy to do it. I don't have any experience with fuel cells. My general impression with fuel cells for wastewater treatment is the size requirements are really large, and with the current state of the technology, not easily implementable. So fuel cell for power, not for treatment. Oh, okay. Okay. Yeah. So again, I'm more on the water and wastewater treatment side and trying to make the biomass and give you a raw energy product. But in terms of fuel cells and the electrical generation part of it, well, I'm interested in that. It's not my primary area of specialty.
Okay, well, I don't see anybody else typing in the box. Well, I guess Brian's got one more comment.
Yeah, for anybody left, if there's something else you want to talk about outline, yeah, feel free to go ahead and send me an email, and we can restart the conversation that way. Yeah, H2 production that Brian asked about there on the last end. There's a couple different ways to get H2 production, and that green box technology that I mentioned as part of the anaerobic digestion it's a nice way if you don't have another use for the nutrients. So we're proposing in the E2Energy to use those nutrients for algae growth, but if you're in a place where you don't have the space for algae growth, or there's some other limitation, then that electrolysis process is a nice way to harvest some extra energy out of a waste that has ammonia in it. So, and then of course there is hydrogen production as a part of anaerobic digestion as well. And then, although it's a small component and it's usually quickly eaten up by the microbes. And then finally, that process I mentioned, catalytic hydrothermal gasification, makes a syngas that is largely hydrogen-based. And so that would be very much like the hydrothermal liquefaction, but instead of making oil, you're making a syngas product, and so that would be another way to get some hydrogen out.
Okay, well, I'm going to go ahead and stop recording. Lance, thank you so much for participating in this. And as I get emails from folks, I will forward those on to you, and also send out a link to make sure everybody's got your contact information that was on the webinar today. So thank you again.
Okay.
I really appreciate it.
All right.